lecture a little bit. So what I want to talk about now first is how can we show in a real system using network emulation what would be the impact on the application? And you already have maybe an idea what could be another method of doing that. How could I figure out what the implications of these new delays? What could be another method that you have already seen today maybe? It's also written on the slide. Simulation, yes, very obvious, yeah, you see, yeah. So, yeah, simulation versus emulation. Who has already maybe simulated a system? Okay, a few people, yeah, great. Who has done something with emulation? I mean, that's a term that many people didn't really hear a lot. Yeah. Yeah, okay, great. Yeah. So hardware emulation, I mean, there's many things you can emulate, yeah. And very often you do that also to bring in legacy software or hardware in a system that should run on top of a system that is maybe long not produced anymore and stuff like this. So at least some people have an idea what emulation means. And I just now want to motivate a little bit why we can also do emulation instead of simulation. Yeah? Because some people would say simulation should be enough for everyone. Then why emulation? What's the difference anyway? Yeah? Between simulation and emulation. So what is network delay emulation? Then I want to talk a little bit, of course, about our tool for emulation, and that's a network delay emulator, which can emulate the characteristic packet delay of a wireless TSN bridge, as you've seen before. That's our goal because that's our subject. Yeah? There's many emulators out there. We are interested in this delay, this specific characteristic delay. And then I want to do a quick exercise with you. Basically, I will be sitting there and typing. You can tell me what to type, but I also want to give you an impression how to use that tool. Yeah? Then maybe you're going home and say, hey, great tool. I also want to use it for something. Or you say, interesting tool. Hopefully you don't say not so interesting tool. So what's the difference between simulation and emulation? So first of all, simulation we've already seen here with Simon. And Simon had applications in his simulation. He had a network in his simulation. He had many things in the simulation. But what is a simulation anyway? It's a set of models. And a model is an abstraction. So the term model is very much used everywhere in computer science. Yeah, I would say that whole computer science is modeling. Yeah, programming is working on a model. Basically, it's not really working on a real world or so. It's a mind model that you first work on. Yeah. Or conceptual model. And the thing is, a model is always an abstraction. It's not the real thing. Yeah? A model always leaves away some details. I mean, have you seen in Simon's application anything about an exoskeleton or a user or any real device or whatever? Not really. You have seen, he said, there's a talker, there's a listener. The one is sending data, the other one is receiving data. What data? Don't know. What are the bytes? Don't know. What is the application doing with that? Don't know. Yeah? So we don't care. We don't know, and we don't care in the simulation, maybe. We just say these are bits and bytes going back and forth. Yeah? Maybe that's enough for us, because a model should be useful. A model always needs to be useful. There is no wrong and right model. A model can be useful or it can be useless. Yeah? And a useful model is a model that helps you answering some questions. Yeah? And a useless model is a model that cannot answer the questions that you have. Yeah? So the abstractions you make is you make this model as simple as possible, but not simpler. Yeah? As Einstein said. Yeah? So therefore, keep it as simple as possible, but not simpler. It's all a model. And that's also the problem. You first of all have to define your model. You have to find your model. Now, if you have already a real application, let's assume you have your exoskeleton, you have your automated guided vehicle, you have a car, you have an airplane or a drone, then you have the real system already. Yeah? If you want to model that, that's a lot of effort. Yeah? Modeling a whole car is a lot of effort. Abstracting a car is also still a lot of effort. Is it real? No, it's maybe abstracted and maybe even wrong at some places. The real deal is the real application, yeah? Or the real system under test. This is what you want to test. But you don't have maybe the real 5G wireless system to test it on. Because it's not existing yet, maybe, because it's just in standardization, yeah? And the real hardware is not existing yet. So what do? You emulate the system underneath and use models there, and you put the real system under test on top. And then you look at your real system under test and see how it's behaving. Yeah? So it's a combination of models and the real system. And that's the lower part is typically called the emulated system. Yeah? That's the model part, let's say. So in networking, and we all talk about networking here, that means that some parts of the network stack are models, and some parts of the network stack, including the application, are real. Typically, the upper parts are more real, like the application is the real application under test, and the transport layer, network layer, data link layer, physical layer might be all models. Yeah? And this is the part I want to emulate. And that's then the network emulator, and on top we run the real application. And then we see as the real application behaves. And if you look at that here in a little example, here on the left-hand side we have a mobile device. On the mobile device we have actuators, sensors, and processors. We have a wired bridge which connects to a wireless bridge. This is our wireless TSN bridge now. That's sort of we want to see what the effects are if you bring that in. And on the right-hand side we have an edge cloud. And in the edge cloud, there runs an application like a controller. And I want to say this is like a network control system now. For instance, this could be an exoskeleton, it could be an automated guided vehicle, it could be a drone, which is controlled from the edge cloud. And in the edge, the controller is running, the sensors and actors are sending their signals to the controller. Controller is doing something on it and sending back the actuator commands to the mobile device. So it's a remote controlled drone or whatever, yeah, or exoskeleton. Of course, wirelessly, because we don't want to pull a wire. But now we already know that by doing so, in the middle, we have delay. And what's the effect of delay on a control loop? I mean, that's a very interesting question. Some people here really are dealing with control loops, maybe. That's a difficult thing. There's what do you care about in a control loop? How should a control loop behave, let's say? Or what shouldn't it do? Maybe online also, if there's someone online doing control loops every day. It should be steady, yeah. It should be stable, first of all. It should not run away, yeah. And it should have a certain performance. Performance in the sense of if you bring in electrical energy, you don't want to waste energy, for instance, yeah. Or you want to keep a certain set point as close as possible. You never want the system to be unstable. If it's unstable, then it runs away, and then hell freezes over. Yeah? So things break. Yeah? And therefore, that could happen. Because what is one bad thing for control loops? Dead time. So a delay between A and B. That could lead to oscillation, that can lead to instability, that can lead to many nasty things. Now, if you have your system here already, why not test it with the real delay? And see how it behaves. Because believe me or not, a control loop is not so easy to model. You can do that mathematically, but guess what mathematics is? Mathematics is a model, and a modeling language, you could say. And you can make mistakes in your formulas. You can leave away things that are important. In the real system, everything is there. It's not a proof, I want to say, but it's at least a good test to see whether everything works with this characteristic packet delay. The question is now, how can we do that? So questions could be, is the control loop stable? What is the quality of the control? Does it deviate from the set point by so much at most? What is the energy consumption of the mobile device because it needs to control the system by the actuators, for instance? How much influence do the actuators need to give to the system to be stable and so on? Or what is the user experience? Even more difficult, If you ever talk about a user, now not talking about an exoskeleton, maybe that's too dangerous, let's say, to take the user and then just test it, But you certainly know virtual reality, augmented reality. I mean, there's a thing called motion sickness. Motion sickness means some people, they don't feel very well after some time wearing such goggles and such virtual reality glasses. Could we figure that out? It has to do something with delay. and something with that the image that you show to the user is inconsistent with what your sensors in the ears are feeling. Yeah? And can we figure that out with a model? I mean, there you need a very nice model of the human brain, maybe, or whatever. I'm not an expert in that anyway, but I think it's a complex model. We have many real human users here. Yeah, I could put a goggle on everybody here, and then we could try it. Yeah, and then after some time, I ask you, "Do you feel well?" That's I know it's an ethical question now and everything, and whoever works also with a company or university, you have to ask first whether you are allowed to do that. And if you ever want to write a proposal, then to be sure that this is dangerous, let's say, and you have to be careful about that and everything. I know, yeah. But what I want to say is have a good model of the human user which can answer you that question. Good luck. Yeah. Figuring that out with experiments, I think this is how they did it. Yeah. I'm not sure whether they did it voluntarily. I just think they shipped maybe the product, and then maybe many users didn't feel very well, and then they figured out, let's say, in the field. Yeah. So what would we need for that to figure these questions out? We would need a model of the application logic, the control loop. We would need physical models of the kinematics of the drone, lifting weights with an exoskeleton, and so on. We would need an energy model of the whole system. Have you ever built an energy model of a mobile device? I mean, if you do that from A to Z, then it's a lot of work that you have to consider and things you have to consider there, from the display up to whatever. Yeah? And the user experience, building a user model, very difficult. If you take the real application, you get everything for free because you have the real system. The physical model is there. The drone flying around has a physical model of everything. Yeah, it behaves like in the real world. It's the real world. Yeah, the only thing that we need is the network. The network is not real because we don't have it maybe right now. So the idea is that we now build an emulator which is able to emulate the network here in the middle, which is characteristic delay, and put the real applications on the left and the right. And then we should be able to figure out what's going on. Yeah. And the question is, how does this look like, this emulator here in the middle? And now it becomes more technical. Yeah, this was all now a little bit motivation maybe. But now I, of course, want to sell you a little bit our emulator, yeah, because we have built such a tool, and I want to show you down to the usage of that tool, how it really works and what we can do with that. What I don't have, just to make sure that you're not disappointed afterwards because I didn't tell you, I don't have the real application. Yeah? Now it would be very nice if I could show you with a control loop or whatever what will happen. Yeah. But we work sort of inside out. We build the emulation tool, and we are not the guys building the application typically, but now we are working also on the applications. We are using the exoskeleton in the project, but this is not ready yet, so not ready to be shown yet, let's say. And you might know some examples from textbooks like the inverted pendulum. You possibly have already heard about that. So a rod that you try to balance on your finger, for instance, that's not tipping over. This is an unstable control system. That it's unstable, you'll see in a second. If it falls down, it's unstable. Yeah? Pendulum normally is stable because gravity will pull it to the bottom. Yeah? So, and that is also something we are building, and then we're seeing how it behaves. But we're more interested now in this here in the middle. Yeah? So, what is that tool looking like? And first of all, our goal was to emulate a characteristic delay of wireless 5G systems. Yeah? There's many other emulators out there. NetM is one in Linux built in, for instance, which can emulate bandwidth limitations, which can emulate maybe other things. But we're interested only in the delay. It's a delay emulator. Yeah? So this is our goal. It was initially developed, credit to the guy who really did it. Lorenz Grohmann did it in a bachelor thesis with me. So he is the guy who really coded everything, and this is important now because I want to show you the real tool in Linux. Yeah, so and it's open source. If you want to download it, if you want to use it, then go to this link and then you can download it and install it on your Linux box. Not a lot of requirements, pure software solution. Yeah. Okay, it's based on queuing disciplines. Who has maybe heard about queuing disciplines about in Linux maybe already? Ah, perfect. it's quite exotic for many Linux users. Still, I would say queuing disciplines is not something that catches your eye at the very first moment when you use Linux, at least. But this is what we use, and I will tell you in a second what it is. It's a very versatile tool, actually, in Linux, if you talk about networking. Yeah. Okay, so some features are it's highly flexible. We can emulate basically any kind of delay. You can write a delay with a Python script if you like, and then bring that in. We are using histograms. Why histograms? We are also using histograms. You can also do anything else, but histograms because we have the histograms, we have the data, and Goro will tell you a lot about that later on. So we have real data from real 5G systems which we now bring into the emulator, and then the Linux box behaves as a 5G network, in terms of delay only, of course. So it's a model. So everything else we abstract away. It's easy to use. It is a user space application, basically, that you are dealing with. It's no kernel programming or so. Because kernel programming, I'm not sure how many people already did kernel programming, but this is a different topic, let's say. So it's a modular design, QDisks. You can combine QDisk in any way. For instance, imagine you can have a QDisk which is doing bandwidth limitations and another QDisk which is doing adding delay. So I can combine QDisk like Lego. I can put one QDisk on another QDisk. Basically, it's a hierarchy. And then I can build very versatile emulation systems. And I can integrate it with a Linux virtual bridge. Basically, what Simon had shown you, I mean, in real world, this is very often hardware switches that you buy from a vendor, and then you plug in physical cables. Like I've seen one here, like this Ethernet cable. Oh, sorry, this Ethernet cable goes certainly to a switch, a hardware switch. But Linux has a software switch inside, and later on in the session about edge computing, we'll talk about that because we need that for virtual machines and connecting virtual machines. Anyway, but we can build a TSN bridge in software completely on a Linux system. So you can even integrate it with that. And then the bridge, the software bridge behaves as a 5G network virtual bridge, which is great. I mean, who has a 5G network at home? No, not a real question. Don't answer it now. But yeah, you can believe me, it's expensive. So, and it's not so easy to set up. And I guess some partners can sell you one in our project. I guess if you can run it on your Linux box, it's maybe much easier to do it for a first try at least. So how does the architecture look like? Very quickly. So here we have a Linux machine. Doesn't look like one, but it's a machine. It's a Linux PC, for instance, so server. There we have a network interface here. This is the part where you plug in these cables. So you know that. And we have a network interface on the right-hand side. Let's assume traffic is flowing from the left to the right. Then it's going into our QDisk here. And QDisk stands for queuing discipline, by the way. Queuing discipline is, again, something like scheduling, like Simon invented. And then it goes into some buffers. And after some time, we take it out of the buffer, dequeue it, and send it to the driver and pass it on. And the delay, the time until we take it out of the buffer here, this is according to the histogram. This is the artificial delay. This is basically this here. So this is this. This should look like this. Packet goes in, then it waits here according to the probability distribution, and then it goes out again. And this is done here in the QDisk, and this is in the kernel. This is in the Linux kernel. This is already there. You don't have to tinker with that. It's already implemented for you. So the only thing that you have to let's say implement is what's here on top. This is a user space application. This is a Python program, a Python application that you feed with your probability distribution that you would like. If you don't like our distributions, which are real distributions from real 5G systems, but if you want to have another distribution, then you can just say to your Python code, use this distribution. Use a normal distribution, use something else, whatever you like. So you just have to modify a little Python code. I don't ask now who has already written a Python script, but I guess all the younger people in the room, and I'm not sure, no offense, I consider myself old already because when I started, there was no Python, there was Perl. So I could not do it maybe so easily, but believe me, every PhD student, master student, bachelor student can do it. Yeah. Yeah, very good question. Very good question. That's already a limitation, I have to say now. Yeah, um, I come to that in a second when I show you why. But the answer is no. Yeah. So we have an identical independent distribution. So we pick it without memory. Yeah. So the one delay is completely uncorrelated with the other delay. This is a real limitation, but there's a reason for this limitation, and the reason is it's more performant if you do it like this, but it's a real thing we're thinking about right now, because in reality, you often have these correlations. Yeah. So I guess if you have one packet which is delayed a lot, then the next packet probably is also delayed by a lot. Yeah. And so there is some sort of memory, you could say, or dependence between the delays. We don't have that. Why don't we have that? Because we have a delay queue in the kernel, which we fill in the beginning. So the delays are pre-computed, yeah, and then you can only do it independently. Yeah. So one delay is independent of the other because you don't know what the other delay was and so on. Yeah. And then they're taking out of the buffer and assigned to the packets. The pro is it gives us higher performance in terms of throughput because this interface between user space and kernel space is critical. Yeah. And a performance bottleneck, let's say. It's always a context switch for the people working on operating systems. So therefore, we want to batch process. We send a lot of delays to the kernel. Kernel takes these delays, sends the packets out, and gets new delays time in batches. Yeah, let's say in batches. But it's a very good point, because is this now realistic? Is the model correct? Maybe so and so. Yeah, but we can modify it certainly. Yeah. Yeah, but I think you get the idea. We need a Python program doing the delay, sending it to the kernel. Kernel is doing the rest. Yeah, and we put the QDisk on the egress interface because this is where it belongs to. It's always before the egress of the box. So we could now build something like this. We have here a Linux system in the middle. We have the host on the left-hand side. This is the real system. This is the real system. We have some fixed Ethernet devices, but the box in the middle behaves as a 5G system. It's a 5G bridge, maybe, because we can combine it with a Linux virtual bridge. Then we have the bridging functionality for free. And the QDisk here, QDisk 1 and QDisk 0, they do the delay for the one direction and for the other direction. So we can have even different delays for upstream, downstream, which is realistic in a wireless system also. So we did also some evaluation just to give you some hints about how good does it work. So we monitor the traffic here at going into the box and when it goes out of the box, and then we measure the delay and compared it to the original distribution that we fed in. Yeah? And this was done with nanosecond precision, so very accurately with hardware, an FPGA-based network monitoring hardware, and wire taps. So it's based on fiber optic cables. And we just look at the optical signals from the fiber optic cables and put it into the monitoring hardware, and they take the timestamp with nanoseconds precision. So the measurement should be quite okay, let's say, and quite precise. And the thing we get out is this. On the left-hand side, this is a curve that we feed in. On the right-hand side, this is the curve that we got out. And first of all, you say, yeah, it's almost the same, but there's a shift. There's a 150 microsecond shift. So we are shifted by 150 microseconds to the right because there's some overhead in the kernel, which is not in the distribution. Yeah, there is no zero overhead in the software, let's say. So the overhead comes on top, and the overhead is on average 150 microseconds. Yeah. Correct. Yeah. Yeah. Okay. Yeah. Very good question. Very good question. The error is sort of transparent for the application in that sense because the 5G system, what happens on an error on the physical layer? We all know on the physical layer there can be bit errors, and a bit error means that a frame is lost, first of all. Yeah. So there's a real error. But what would then the MAC layer do? It would retransmit. And it would retransmit again if it's again lost. And I think Goro will talk about that a lot. But what shows is that a lousy link, let's say, a link with lots of errors, will show as a link with a long delay. Because at the end, what you lose is just a lot of frames that you have to retransmit until finally, eventually, they are received correctly. So we did measurements in Wi-Fi systems and they all have automatic repeat requests. That is what it's called, ARQ, automatic repeat requests. And in 5G, it's a hybrid automatic repeat request. And they sort of mask these errors, but translate the errors to a delay because they have to retransmit again and again and again. Of course, there's a limit to that. If the link is really, really bad, then of course your connection breaks down. Of course, yeah. Yeah. Yes. Yeah. So data error model is not uniformly distributed. You have the birth errors and all these. Yes. So I'm a little bit hesitant to accept this answer as that's really how we do it. Yeah, yeah. Yeah. Exactly. Yeah, yeah. Very, very good point. Goro will talk about it later on very much more in detail. This is the first step. So here we talk about a stationary distribution, yeah, which is not changing. This is what our tool can do. This is not our assumption in the project. On the contrary, KTH or Goro, as he will present later on, they are doing experiments in various environments where we have, and they especially deal with non-stationary distributions. And we have also a concept, especially also for end-to-end scheduling. I'm pointing at Simon because he's doing the end-to-end scheduling part in our project, where we assume that a network needs to inform the central entity, which is the centralized network controller. The people who've heard about the TSN talk in the beginning know what I'm talking about. Let's say the intelligence of the network needs to know that the distribution has changed. And then we can readapt, for instance, the scheduling for the real-time traffic. So we don't assume explicitly a stationary distribution. On the contrary, we have adaptation concepts. We have, going down now very in technical details, Yang models in the bridge, which can say this is the current distribution and can notify us when the distribution changes. Now the question would be, I'm taking in advance already your question because that comes up of naturally, how fast can you do that? Yeah, if you talk about fast fading, slow fading, and stuff like this. Yeah, so here when we talk about end-to-end scheduling, this is our job at University of Stuttgart. Then our algorithms to calculate a new schedule, they have a runtime of at least seconds. They cannot do that in a millisecond. Yeah, this adaptation level is done in the 5G system already. If the 5G system would adapt fast enough, we would see again maybe a more or less stationary distribution because the error rate would not change. Now we would need Joachim Sachs here from Ericsson to back up my claim a little bit more. But I think this is, from my perspective, what you would see. But this is another level of adaptation. So what we assume is we can have changes. We even predict the changes based on the data. I think Goro will also talk about that. Sorry, Goro, that I'm talking maybe already about your part already, but we have a prediction how the distribution would change over time based on machine learning. Yeah? And Goro will talk about that. So let's say I gave a lot of teasers now for the talk by Goro about exactly this topic. But don't confuse this tool now with our general assumptions in the project. This tool is simple. This is a bachelor thesis tool that we developed here, yeah, which helps us a lot already to figure out in a stationary distribution how the application would behave. But the dynamic case is much more interesting, but requires a different tool and requires the concept that we're right now doing measurements for and concepts like prediction. Yeah. But a very good comment because this is a shortcoming of the tool, actually. Yeah, definitely. Having said that, it's a good tool. Yeah, don't get me wrong. So I think even doing that for the stationary case, if you have a control loop and you try to figure out the stability of a control loop with this distribution, even if you do it for the stationary case, it's not so easy to do it, let's say, in a analytic fashion, let's say. Yeah. Okay, here you again see the two curves overlaid. The one is the green, the other one the blue. You see the difference of the tool. There is a difference. A projector is kind enough to mask that difference because you cannot see it because of the projector quality, but you see it rightly shifted to the right a little bit. Yeah. Okay, so There is limitations, and here it's exactly the limitations that we have talked about also somewhere, I think on the next slide. So dynamic, non-stationary delay distributions only at a very, very coarse time granularity. We can change the distributions, but it would take at least seconds until you see the effect. So non-stationary distributions are not well supported by the tool. Because of this buffering, if you buffer a lot of packets, you can do the math how long it would take until the new values would appear in the buffer. So you have a long dead time if you talk about a control loop maybe or so. There's also performance limitations, so it's a software solution, be aware of that. Everybody developing FPGA or whatever, it's not at line rate, or let's say it's not at 1 gigabit line rate, or hardly at 1 gigabit, it's maybe 100 megabit more than 1 gigabit. It's certainly not 10 gigabit per second throughput. I mean, if you ever try that with UDP sender on a Linux system, it's impossible anyway, more or less, unless you do some very fancy thing like kernel bypassing or so. Okay, so now I want to switch to the very practical part, but before I go to that, is there any more questions about, let's say, the concept or the tool or whatever you have in mind? Okay, we have another talk about the distributions anyway, and Goro will present you lot more details about the distributions and so on, and the measuring of that, and much better than I could. Okay, so what I want to do is, if you want to join, you can do that, but I want to just show you, and you can maybe follow with your eyes or on your keyboard, how we emulate now the delay in a virtual machine. And for this, I should tell you there's some basics for getting the tool running. You first of all have to compile a kernel module. If you download it, read the README file. That's always the first place to start. But you need to load the kernel module with that command. We do that in a second together. And then you can add the QDisk. And you say, see the QDisk has some parameters. Maybe I can explain them first before we do that practically. You can say the name of the QDisk, which is always delay. That's the name that we had in mind. You can say whether it's reordering or not, because if you pick delays independently, so IID, if you pick delays IID, there can be packet reordering. Now, there could be another question asking, is that realistic? Is it really realistic that the MAC layer will reorder the packets, or the frames, even if you do automatic repeat requests? And the answer is probably not in many cases. And we can have a switch, which is then saying avoid packet reordering, but that would mean you also change the distribution a little bit, because then you would not allow for a long delay followed by a very short delay. That is the trade-off. You alter your distribution. And there's a limit switch to say how many packets can be buffered, and when there is an error message coming up when the buffer runs low, which is not so important maybe. So the user space applications may be more interesting. It communicates with a kernel through a character device. This is this def scheduler delay, and then the name of the network device with a major and minor number for the QDisk. This is the file that you write to the kernel for saying this is the delays that you should use. And every programmer can do that, I guess. So you don't even have to use Python. You can use whatever you like. You have to open a file and you have to write the delays to the kernel, and then it's fine. In the right format, of course. But anyway, it's not too hard to do. And for this, you need this file. And the file is always the name of the network device with a major and minor number. And talking about versatility, you can also combine our delay QDisk with other QDisks. For instance, there's an ETS QDisk, which is the enhanced traffic selection. Simon has talked about traffic selection for TSN. This is existing in Linux, the enhanced version of the traffic selection specified sort of by IEEE. And for this, you can have different traffic classes and apply different delays for different traffic classes. So I can classify my traffic into class 1, 2, 3, and I can give one delay to class 1, one delay to class 2, one delay to class 3. And this is, you could say, the one is priority 1, priority 2 traffic, priority 3 traffic, and they have different delays. You can also have that in a 5G system, for instance, different quality of service classes. So you can do that and combine it with any other QDisk that you find. And Linux comes with a lot of QDisks. I don't want to talk too much about QDisc for Linux. I want to show our tool. But you can build a hierarchy of QDiscs. We don't do that now in our little demo, but this is how you would do it. You need to have a root QDisc, and then you put the other QDiscs underneath. Quite intuitive. Not in terms of syntax, I admit that. I give you that the syntax is not very intuitive. But this is the Linux syntax, so I can do nothing against that. We can build hierarchies of QDiscs using filters, and the filters to build the classes that you want to give different delays to can build on anything that you can see in a packet, on all header fields. IP address, port number, MAC address, you name it. So you can say MAC address so-and-so is priority 1, MAC address so-and-so priority 2. Okay, so now comes the practical part. And you have to bear with me a little bit. Now we're doing a tutorial. I would like to do it on real hardware. And I would like to show it with real applications. The only thing we can do here is now we run it in a virtual machine. The good thing is you have the virtual machine. You can follow me and you can run the tool as I do here. But it's running in a virtual machine. It's not nanosecond timestamping hardware inside or whatever. So the distribution we get out at the end of the day, and I can predict that already, will be not so smooth as the thing that we've seen before, because we're running that in a virtual machine on real hardware, in software, and so on. So you could blame the virtual machine on that, but it's convenient to do that. You can run everything on one PC, but in reality, you would set everything up on a dedicated machine, of course. The delay emulator would not be the same machine as the talkers and the listeners and the end system and the application. So what we want to do is now this here. We want to set up a talker on the left-hand side, a listener on the right-hand side. Obviously, talker is sending to listener, and we want to delay the messages from the talker to the listener with our delay emulator. For this, we have to bring in our QDisc, and on which side do we have to bring it in? At the egress side of the talker. Because QDisc always work for packets going out of an interface, not for packets going into an interface. There's only one QDisc, which is called ingress, which works from the ingress of an interface. So it works on the outside, on the egress port. If you want to delay the messages from left-hand side to right-hand side, we have to put the QDisc here. Therefore, this figure here. And since I only have a virtual machine, which is basically one host, we have to isolate the applications that we have the feeling that they cannot talk to each other directly. So it must go through this line here, through this cable. It's a virtual cable, of course. And the way I do it, I use Linux namespaces, network namespaces. Who has already heard about Linux network namespaces? Okay. Who has already heard about containers? Linux containers? Many people, okay. This is exactly what containers do. Containers are based on Linux network namespaces. And what this is doing is it isolates a certain space. Let's say in the kernel, it's one kernel, but it isolates the one container from the other container. And this is based on Linux network namespaces. We do it manually. A container software like Docker would do it automatically. And then we pull a cable from A to B. This is a virtual cable. And you will see we can pull a cable in software. Sounds interesting, but it works. And this is also how every virtual machine would do it if you want to attach a virtual machine to a physical network interface and stuff like this. Okay, having talked a lot about that, let's go to maybe the practical part. I hope you can read that. Is that okay? I can even make it even bigger. But the bigger I make it, the less is on the screen. I take that as a yes. It's a silent consent. Okay, so let's start. What do we do first? We create a Linux network namespaces. And we do it manually by hand. And as I said, you can follow me now, or you can just later on watch the video and repeat it with stopping the video and so on. So the tool for doing Linux networking and configuring a network interface on the network layer, data link layer, is always IP. Don't confuse it with the IP protocol, which would be network layer, but the tool in Linux, the command line tool, is always IP. So I can use IP on the link layer. So then it's called IP link. Then it shows me all the network interfaces of the machine. I can say IP address. Then it shows me the network network layer information, the IP addresses, for instance. I think everybody can identify the IP address here, and so on. And there's another option to IP, which is called NetNS. And NetNS stands for network namespace. So we first create a namespace for the talker. Looking here at our figure, we create here the blue box, the light blue box on the left. Then we create the light blue box on the right. Then we create a cable between it. Okay? That's how we start. That's long, not the end, but this is how we start. So sudo IP. IP is the command line tool that you always want to use for networking. Net namespace. Add. It's very intuitive, isn't it? It's like reading a sentence. Add, and then we call it talker. So that's the talker namespace. Okay, and the password for the user is Debian, if you forget it. Sudo, because everything is now anyway on the root level. We also need one for the listener. So we add another namespace for the listener. Now we can verify that everything is here, net namespace list. And we see two network namespaces, listener and talker. Yeah? So far, so good. Next thing you want to do, and I should have mentioned that if you want to speed up everything, of course, you can also do copy-paste from the slides or from a file that is also in the virtual machine. So we have done this here. Next thing is you want to connect the namespaces by a cable, by a virtual cable. So how do we do that? A cable is on the, I know a cable is on the physical layer. Yeah, so but above the physical layer is the data link layer. So we create a data link layer cable on the Ethernet layer, let's say, from the one virtual machine to the other. And for this, we use virtual Ethernet devices. And you create a virtual Ethernet device always in pairs. So if you look at this here, you see sudo IP link add. Virtual Ethernet device talker is one side of the cable, and it's of type virtual Ethernet, and the peer, the other side of the cable, is virtual Ethernet listener. Okay? So this creates a cable from let's show it here in the slides again. From here, from this interface to this interface. They're not yet in the namespace, but this is what we do. Okay, so now I should maybe also to speed things up. Here's the right one. Let me just do a little trick, which you can also do, by the way. Yeah? You can go into this training day folder, and then you can go for the tutorial delay emulation, and there's a README file. And in the README file, you will see all the commands that you have to execute in sequence. And since okay, I can type reasonably fast on a keyboard, but not on a laptop keyboard. And there's many things I'm missing here, unfortunately, but what I do is we make it copy-paste. Yeah? We would need another tab for that. And then we have, yeah, a little bit slow, but it works. Our command here, so we do that. Password. Okay, so when we now say IP link, we should see there's a new Ethernet device, virtual Ethernet device listener, and this is attached to virtual Ethernet device talker. So the cable is now here, okay? But the cable is not attached to anything yet. It's basically existing, and it's not attached to the network namespaces yet. So what we want to do next is we go here to the network. Oh, okay. So this is first. So we assign the virtual Ethernet devices to the network namespaces. That means they will disappear from the root namespace, and now they will go into the network namespace, into the container, you could say. This is exactly if you start a Docker container and you see an Ethernet device, this is an Ethernet device inside of the container, which is not visible outside of the container anymore. Therefore, it's called namespaces as in programming. Yeah? So So this is the commands, very intuitive. Sudo IP link, we are on the link layer. We set the one Ethernet device into the talker namespace and the other one into the listener namespace, okay? So if I can do that by heart on the first try, let's see. Sudo IP link set Ethernet device listener net namespace, and that should go into the listener namespace, I guess. Okay, and the other one goes into the talker namespace. Fair, simple enough. So if I look now here at my Ethernet devices visible in the root namespace, they are gone. So they are now in the namespace. I cannot see them anymore. So how could I go into the namespace? How can I execute a command in the namespace? Because for this, it would be visible again, the device. That's also very interesting. So it's again the IP command, IP net namespace, exec for execute. And now I can say any command I want to execute in the namespace. First of all, I have to say in which namespace, the talker namespace. And I simply say bin bash. And you know, this is a terminal, it's a shell basically. And this shell is now running in the namespace. So if I execute that, then I'm the root in the namespace. And if I now look into my network devices in the namespace, you see the talker device there, because in the namespace, it's there. Only outside of the namespace, you don't see it anymore. And I should do the same thing, of course, for the listener. So net namespace, execute in the namespace of the listener, bin bash. See, you also learn a lot of Linux. This is nothing about the emulator so far. So everybody who has already knowledge of Linux, sorry for that. It's a repetition, I guess, for you. Okay, so the interface is also there. To make it a little bit more interesting, can we already, let's say, communicate from application to application over that interface? We have a namespace with one network interface. We have the cable connected to the other namespace. If I want to ping the other namespace, would that work? If I want to send a UDP datagram to the other namespace, would that work? Maybe in the chat. Simon says no. And that's right, because something is missing. We are so far only on a data link layer. What would you need to communicate in an application via one socket with another application on the other socket? You would certainly need an IP address, and actually you also need a port number, but a port number has nothing to do with the interface. So we need to assign IP addresses to our network interfaces now. And I hope I can remember that, but the command is IP. What else? IP address now, because we're on the third layer, on the network layer. We want to add an IP address, and I say it's 10.0.1.1.24. If that sounds Greek to you, then forget about it. It's just an IP address. And I want to assign that to the Ethernet talker device. Did I forget something? No, I don't think so. Oh, it's duplicated. I shouldn't use the same. I forgot something. I should add device. Yeah, very good. It's not so intuitive. Yeah. So if I now look here, IP address, I see we have now our Ethernet device with an IP address assigned. Yeah. But it's still down. It's somewhere written that it's down. Where is written? Down here on the right-hand side. So that's a little bit cumbersome, but we have to bring the interface up. So IP link set v Ethernet, where we are, talker up. Okay, now the one side is ready. We need to do the same thing on the other side, of course, with a different IP address. IP address add 10. Of course, same subnet would be good, wouldn't it? Listener. It's called Ethernet listener. And then we also need to bring the interface up. IP link set VF listener up. Okay. So what we have now is just a connection from the one namespace to the other namespace, which should work. Let's check it first. And before it doesn't work, you see it works. We can communicate from the one namespace with the other namespace. But this is not what I wanted to show. This is just a little bit the story around it, maybe. What we need now is, we have done this here. We have done this here. We have done this here, and it works. So now comes the interesting part. Now we add the delay emulator. And as said, the delay emulator, if you look at our figure, it should be added on the talker side. Yeah? Therefore, we do it now from the talker namespace and add the emulator there. First of all, we need to load the kernel module. It's pre-compiled. It's in the network delay emulator schedule delay build folder. I hope it's there. Otherwise, we need to compile it. So the command is called insmod. And it's actually no, that's doesn't matter from where I execute it, but better do it here from this side. Insmod. It's a wrong user. Home, Debian, network delay emulator. So build, and then it's schedule delay co. So that's the command, loading the kernel module. If you never have loaded the kernel module, very good. But if you want to do it manually, that's the way it's done. Insmod is inserting a module. rmmod removes the module. Yeah. So now it's loaded. The module is loaded. That's good. Continue doing that interactively. I would say we have 3 more commands to add. And I leave it as a homework, sort of. And if someone manages to do that and send us their, let's say, histograms or their output of the end-to-end delay, you will get the Distinguished Training Day Award or something like this. Let's see. But it's not much to do. It's just here adding the QDisk. That's one step. And then there's some boilerplate things to do, like user space, application starting, adding the delay, and then measuring it. That's it. Then the base setup is already